I am going to talk to you about this is what I call the crash course in organic chemistry. I decide that it is a 001, the part B. Okay, so that's the one that I am going to do. I just want to quickly go through and just to give you an overview. The nomenclature is very important, and make sure that when you guys see the EN means ethylene diamine, OX means oxalate, and that's something the EDTA, even I don't know the full name unless I have to look up, but it is a one that the ligand is the one have the lone pairs. They are the one that essentially it's like a docking to the central metal atom. Okay, metal complex. The metal is at the center, and they are the one playing the usually positive charge, and they are looking for lone pairs. So this one is the COOH. So those are the carbonate group. They can form they can give out the lone pairs. So this is like to me this is like 2, and this is an amine. They are like 2. This one is they are 4. So this is very strong, very famous ligand can have a 4 dandate. Okay, and nomenclature-wise, it can be either anions or neutral, and then anions. Make sure that you are seeing this something at the end as an O. A bromochloro is a easier, good example to understand. Neutral has its own name. Okay, aqua is a water, amine is for the ammonia, carbonyl for the carbon monoxide. Ethylene diamine is ethylene diamine. The thing that I find is funny is if you look at the EDTA, it is a -4 charges here, right? You see the -4 charges there? I don't know why they put in a neutral molecule. The name speaks that it is a negatively charged molecule, right? And then, but I think that they made a mistake in putting in this wrong place. This is a slide that I made a copy for you guys to have a look at it. And I want you to work on the nomenclature. I worked on it last time before. So this is something that I want you to get familiar with. The unique nature of the IN, which is ethylene diamine, and I usually put it in something it looks like this kind of pictures. Okay, so this one is trying to represent 2 lone pairs and the 2 lone pairs from the nitrogen. Okay, so those are the one, and then it has a CH2 bridges going across it, but it's almost like somebody with 2 hands. Okay, they're gonna go and grab it with a 2 and so when you have seen this cobalt sitting in with an in means so you have 2 hands, right? And there are 2 of them. So effective number of coordination is is 4, and from chlorine is as effective as just a simple 1, and there are 2 of them, so there are 2. It is a 6. If you have a 6 coordination, this will be an octahedral. Okay, octahedral means it looks like as shown in this figure that's shown. You have a little plane. It's a piece of paper sitting it in, and then there is something sticking up, and there's something sticking down, and the cobalt is sitting in the center. And I am going to highlight I guess when you have this, particularly this case of the metal with En2 and then let's say chlorine 2, and if this is a metal complex case, this is a one that having essentially octahedral, just like it's shown in the below, but chlorine is a position that are there in the same side. So if I put a chlorine on this side, just like the same picture showing up above, and this is a geometric isomer called the cis isomers. And if I put the chlorine in the opposite side, okay. So here, deliberately, I'm going to put chlorine here and chlorine here. This is a trans, okay. And this is for me they are essentially, if you imagine the plane, they are in the opposite side. And if you have these two and then kind of flip this way, and you can find yourself the chlorine is on the opposite side. So what is important is trans is an easier to identify. They are the opposite side. Cis is essentially your neighboring side. Okay, and so that you can do that. And if somebody put it a chlorine, I will put a different example of the cis isomers here. If somebody even put a chlorine here and here, you can see that they are essentially right angle, right? So they are. This is an example of the cis, as well as showing something shown up here. And you can look at your slide on. Then I explained this a little bit more details before in my crash course number 1. If you see that metal with an En 2 and chlorine 2 or bromine 2, and if it is a cis, and they can have optical isomers. Isomer possible. Okay, what that means is if you have a trans metal ethylene diamine 2, chlorine 2, effective number of coordination is 6, optical isomer is not possible. And that's what this slide is about. Okay, and also this is a slide that I want you to refresh your memory. That go to your lecture slide in here, and if you have a metal with a En with 3, that's the same as the effective number of coordination is 6. This one is actually optical isomer possible. And as I mentioned, that optical isomer is somebody saying that optical isomer is a chiral isomer. Somebody saying that enantiomer. They are the same thing, okay? And even I added up something like optical isomer is the same thing as a mirror image isomer, okay? Hardly anyone saying about this way, but it means the same. Okay, these are the same kind of class. Mirror image isomers, enantiomers, chiral, and optical isomer means the same thing. Okay, so I talked about geometric isomers in this example, and this is also, as you can find out, this is coming from the slide, and I'm going to be speed up a little bit compared to my previous version number A in this crash course. So just think about if you have a 2 ligands, and this is a geometric isomer is what we call the cis and trans is the term they use. If you have a 3 identical ligand, and then FAC and MER isomerism is what they choose. So here I have given you an example of is a metal with a 2 ligand, and the B is the one that I highlighted here. That's the one that's kind of easier to keep track of. And if this one is something looks like that, and if this is a tetrahedral, then they cannot form cis and trans. But this one plus square, okay. This one plus square planar, and so that means you have essentially this plane, okay, and then you have you can just I will just simplify A and A on the same side, or to be consistent, let me just focus on the B, okay. So if I have that and the B and B on the same side and the metal sitting in the middle versus B and the B in the opposite side and the metal sitting in the middle, obviously this is neighbors cis, and trans is my thing, the opposite side, right? And this is a square planar, and the square planar is coming from the geometry from actually same class as an octahedral, which is very common there. So what I mean is they kind of didn't show you that you have a 4 coordination, right? 1, 2, 3, 4, and you have actually 2 lone pairs that is on the axial axis. This is what you learn in the Basper theory in there, in the Chem 1. And so this is if if I put an A here, this is redundant, but that's a trans and that's for the cis. So for the square planar is an octahedral geometry, and it just you have a four atoms are making a coordination with the metal, and is an invisible coordination. People don't call it coordination, but invisible two orbitals, lone pair electron on the axial position that make up the square planar. And when you have another type of geometric isomer, so this case is pretty obvious that you have a 6 ligand, and the 6 ligand case you always have a 6 ligand, right? 6 ligand and octahedral. And octahedral make it almost like a habit, right? This is an octahedral, and then you can put something that axial position. Okay? This is a piece of paper, then that you put axial one, and then one is at the down at the axial position. And if I put this one to here, and then I focus on the B, so let me just do the B. So if I just focus on the B, if I put a B there, so I can choose anyone. Okay, so I can choose B here, I can choose B here. They're on the same side, whereas you can, if you put the B here, they are the opposite side, right? So this, when you have this MA4 B2, it's easier to keep track of these two, whether they are in the neighboring side or not. And this is a cis, this is a trans. And the geometric isomer for octahedral metal complexes, this is a FAC, and an MER isomerism is pretty unique. So this is a case when you are dealing with something looks like this, metal with 3 ligand and 3 ligand combined, and an FAC means a phase. Okay, and so that's they're forming this kind of the faces here. Essentially, this is a cousin of cis. They are on the same side. But if you're looking at the MER, they call it through the center. MER means that actually the meridian. And if you look at my previous video on the YouTube, I explain a little bit more details. It's going through the poles. So this, if you look at that, this is like going through the one. So if you think about, there's a fruit here, and if you go through it, that's an MER. But if you have a side on the side, and then that's a cis. Okay, so let me do the practice one more time here. Okay, octahedral, draw the square plane and put the axis upside down, almost like a piece of square paper, and then put an axis upside down. An interesting perspective is when you have this one and put this another position, you will see that. I mean, I can give you some interesting perspective. I give you this another. This green plane, can you imagine this? This one, and then this, and that. And if you can see that, that's on another. So what used to be a plane here, and then these things are sticking upside down. And this figure means you're putting a plane here, and this one's sticking upside down. So whether you do it here, whether you do it there, it is the same kind of form. So remember that. And then now we are going back to the original argument. Okay, when you have a B3, so the three compound, you can put B here, B here, B here, right? So you can think about this is forming a faces, one of the faces of the pyramid, actually probably putting upside down. Whereas if you have so let me put a little bit different notation that what I shown up here as an MER. So MER is going through essentially, and so MBC. If I put B here, B here. So this is a key component, and then you can take anything here. If I put it here, we are talking about the plane that is on this black piece of paper, right? But with a border line, right? So this is an MER, which is a meridian and going through the poles. And then this is an FAC when you have a 3 coordination. So those are the ligand And this is you can go and look for the lecture slide. Just looks like that, and then you guys can learn it more. Linkage isomerism is something that is not so clearly discussed, but I think it is also something that offer the complexity that you can see. And here's a picture that I was able to find out. And but I would like to start with something that is a little bit easier to understand. Okay, so let me start with this. There's something called thiocyanate. Okay, this is a cyanate, and thiocyanate means the sulfur cyanate. Okay, so that's what it means. And if you draw the Lewis structures, this one is the triple bond and single bond. And just like sulfur and an oxygen are on the same column in the periodic table, they like to have satisfied octet rule. They develop the negative charges on there. So when you see that, this is a negative charge for the thiocyanate. But if you look at that, this one satisfies the octet rule. This one satisfies the octet rule. The nitrogen actually does have these two, okay, and the lone pairs. So now what you see here is if you blow it up, this one have lone pairs here, right? And also they can have lone pairs there. So it's almost like two heads. So if I have a metal complexes, okay, so if I have a metal complexes, and I'm just let's say if they form the octahedral, and this one can be formed in a way they can offer coordinate with the lone pair electron with sulfur is going in, and then this one is like this. Okay, so that's one of the linkages. Or the other one is this is one of the unique thing about the inorganic chemistry. In this case, if they can provide the lone pair electrons, but now the nitrogen is coming in, the carbon and sulfur. Okay, so these are the two cases. Okay, so because of the whether there's a lone pairs in the sulfur or there's a lone pairs in the nitrogen, and which is more common? What do you think? Anyone? Oh, we have 12 people, so it's a little bit. Well, there's one more person coming. Okay. And this case is we call this when this lone pairs on the sulfur is making a coordination with the metal center. We call, as the name suggested, isocyanate, cyanato. I mean, if you put it in the name nomenclature like that, and then this one is actually, it looks like if you look at here, right? These are two that looks like a cousin. Essentially, whether you're putting a dog here or you're putting a dog in the other like your butt side, right? Your front side or your end side is coming make a coordination. So that means chemists using this notation called iso. Iso means a cousin. They are related. So cyanato is if you put in a ligand because it's a negative charge one, right? So they just put an iso means that they are related. And which is more common? I would say this is more common. If you remember, if you ever look at the discussion problem, actually there's a problem on the thiocyanate. And this is actually, they kind of assume that this is a more common here. Okay, more common. But this one is also possible. Okay, so that's a pretty interesting argument here too. And another example this is what is called the linkage isomer. Okay, so due to atom connectivity differences of the ligand to the metal. Okay, so metal. And there's a ligand, and ligand can be represented by this lone pair electrons. And which lone pair does it go? And this is what is known as a nitro group, and this is on another example that I can spend. And the nitro is an NOO, okay, NO2 with a negative charge. And if you start to put the double bond, okay, that's good. Single bond, and these are the Lewis structures, and that's a negative. And then, okay, so this is a 1, 2, 3, so you need the lone pairs here. So, and then this one is having a resonance structure. Say, okay, I can have a double bond here, nitrogen, and an oxygen here. Okay, so they have a resonance structures. Okay, so in this kind of the argument here, this is a nitro. You can essentially think about, this one is essentially nitrogen sitting in here, and oxygens sitting on connected like this, and the negative charges are distributed like this, right? And then there will be enough, I don't know, I cannot put all I mean, I have to choose one side, so I guess I have to choose on one of the side. But the other one, essentially charges are being spread out, and they are the lone pair electrons. So let me do the same kind of a color notation. So if you look at here, so let's go back to the original. Okay, I forgot to put the lone pairs here. So if you look at going back to the original, so this is a lone pair that can form the dot, right? Just like a dot with a metal complex in the middle. So this can be shown as a ligand lone pairs. Or if you look at that, you see, this is another one that can serve as equally as the lone pairs here. So depending on whether they are, so if I draw the picture like this is almost like a kite-like molecule, right? This is almost looks like a kite, like a triangle, and whether this one is docking to it or this one is docking to it, you have what is called a linkage isomers. Okay. Okay, so I think this one bothers me, so let me get rid of it. And so, when you say the nitro versus nitrito, okay, and nitrito is this notation. What they trying to write this one to emphasize these two, to emphasize, if you see here, the other one, the nitrogen is docking to the central atom, whereas an oxygen is linking to the central atom here. So if I actually kind of finish up, there are two lone pairs in here, right? And this one this is same one nitrogen, two oxygens, and there are also the lone pair electrons available. But what they choose is, this is the one that making a coordination, and this is an oxygen making a coordination, because that's the one that is really the docking, right? So docking means a linkage isomerism. And this one we call the nitro, which is more common. And this is some sort of the cousins of the nitro and nitrito, okay? Nitrito, okay? And this is less common. Nitro is more common. I think that I mentioned in my Chem 1 class, have you guys heard about TNT, right? Trinitrotoluene. That's a TNT, so the name comes from. The nitro is a more common name, functional group. Okay, so I think that we have ample time for discussing about a little bit more complex the energy diagram. So this time I have to talk to you about this something called the energy diagram, and this is what it is. Okay, so let's have a look at it. This, you have to start from here. So d orbital, there are 5 d orbitals. There are 5 d orbitals, and then what you can see here is I am going to color the d orbital into two categories, which is this one and this one. Okay, so these are the two d orbitals having the similar kind of tendency. And what do you think about that? What do you think about that? So do you see the x-axis here, y-axis here, and z-axis here? This they call it the z squared d orbital, and x squared minus y squared orbital. This square means that they are on axis. So these are the one. They are on axis, right? So that geometrically they are. And then if you look at the other one, so I'm going to put in a different color. So these three, they are in between, right? I don't know how to call it, so I would just call it as in between. As name suggests, dxy, dyz, dxz. So they are the one, if you look at that, and they are essentially in between the axes, right? And this is easier to see for you too. So that gives a very interesting argument about energy splitting, and now you can kind of follow what they're trying to do. So these are the three. They are in between, and the one and the on the axis, okay? And this is a one d g square and a dx square minus y square. So this is just a geometrical one. Okay, so now we are thinking about having the coordination. So let me give you a generic diagram. So I think that I'm going to follow the same notation that they shown up here. Okay, so this is an x, this is an y, and this is a z. Okay, so this is an x, y, and z. And then now I'm going to put a little fainter colors. So you remember I draw the tetrahedral all the time. So this is your piece of plane, and this is your axial position, and this is your bottom position, right? So that's what it is. And then we are going to put the octahedral, the case of the octahedral. So that's the case of the octahedral case. So what we are talking about here? In the octahedral case, we are talking about ligand going up, going down, going on the corners of those. So those are the octahedral case. So what do they do is they are essentially pushing the lone pair electrons by coordination. It's almost like a squeezing the electrons to the center. At the center, what you have is a metal is sitting in the center, and that's some more scenarios. So therefore, the one that is having this feeling, quote unquote, feeling this lone pair pushing by the ligand, and the other one energy will go up, okay? And then the one that, so this is the one where energy will go up, whereas the one in between, when these electrons are being pushed, and these are the electrons are being pushed, this one is less squeezed. So the energy level, this one is relatively goes down, compared this one go up, right? So because when you do that, this one is you are really pushing the lone pair electron against the d orbitals, and that's unhappy scenarios, okay? And so this is a diagram that the orbital energy split. That's the one in the case of octahedral, and you can see the g square goes up and the x square minus y square because they are on the axis, and the octahedral, the ligand is essentially providing the lone pair electron, the pushing the electron. There's an electron repulsion, and so the energy levels go up. And so therefore, this one is relatively didn't go up that much because they are the in-between. And this energy is trying to say that if you just leave the d orbital alone, just like on the left and right-hand side, it is energy level is like this. But if you start to put the lone pairs and pushing the lone pairs toward the d orbital, the energy level goes up is pretty mild, whereas this one is pretty much steep rise to go up. So this is what is called a delta, and they're using this symbol delta as an energy split, and the octahedral split is the pattern 2 at the top, 3 at the bottom. And which one determine the essentially the delta? Okay, so the delta is 1. So this is a delta is how much is 1? How much of the energy splitting do you have? And the delta large. And this is a case when you have seen the larger increase, and this is a delta small. And this is a case where you are seeing the ligand is not pushing the electrons so much. Okay, so probably the weakest one is an H2O. It is a neutral, and oxygen is there are lone pair electrons right there, but it is very weak. Okay. This notation is confusing from the lecture note. This is the weakest. Okay, this is what that means. The weakest, the most less effective, but they can still form the coordination. The one that is really hard, I need to highlight is this. This is a CN minus cyanide group in the nomenclature cyano, and it has this. This is looks like a torpedo. Is very, very strong. It has a polarity in it, and it has this lone pair that is that loves to. Actually, the former charges on the carbon side, not the negative side. Oh, okay, let me try not to delete the important one. Okay, so that's the one, and this is a very, very strong. Okay, so this is a very strong one case where you're going to have a large splitting on this. Okay. And I like this that the problem, this is a problem, the optional problem in your class where this has been discussed. And then what I can do here is this is okay. So first thing is this is weak ligand. Right? Oh, this is a strong ligand. And then the Fe. Okay, this is a neutral, so no charges, 3+. So this is an Fe with a positive 3 charges. And if you're looking at that, actually, this is a Fe 3+ is argon with 3 d5. You have a 5 d orbitals surviving in this scenario. Okay, this one is a -6, but this is a -3. So this is the same scenario, Fe 3+. Once again, this is the same as argon with D5. Okay, 3d5. So we are talking about the comparing these cases. Essentially, this problem suggests that you have a Fe. Ion charge +3 ion sitting in the center and coordinated by weak ligand or the strong ligand. And then what the diagram that you should do is, once you figure that out with the weak with this, so I know the octahedral, the d orbital should split, and this one will split like this, whereas the strong one they will split just like that. Okay, so delta is a large, delta is small for octahedral splitting, right? So this is an energy. And then you need to put essentially 3d5, 5 d orbital electrons. When the energy is, let's start from here. This is a little bit easier to understand. So you put first 2, 3, and then when you're trying to put the fourth one, and there's a pros and cons going up there, and you have to overcome this much of energy, and this is too much of the, I guess, the energy they have to pay. So I don't mind just pairing up. So this is what they're going to have for the case of the strong ligand coordination. When you have a weak ligand coordination, first thing is, I have 3 electrons sitting up like that, and the fourth one is they actually prefer this, because they can have a spin up. So spin-spin coupling is what they can favor. So this is essentially 5 on spin on the electrons. So that when the case for the weak ligand, and they are going to have a maximize their spin state. When there is a strong ligand, they actually do not, instead of making us causing the spin coupling, they actually spin pairing so that they can actually stay in the lower energy state for that purpose. So as at a net result, what you see here is this one, this compound, which is Fe aqua, hexa aqua ion 3 complexes, and then this one has a larger spin, electron spin state, and then what that means is this is a stronger paramagnetic. Okay. I'm not saying that this is a diamagnetic. This one is a paramagnetic too, but this is just a weaker paramagnetic. Okay, so this energy diagram is very powerful for you to think about. And then I actually take a little bit, carry a little extra mileage here. And what about the tetrahedral split? So this is the same d orbital. Now think about this idea. I kind of talked about x, y, z, and then these are the axial positions. And but tetrahedral, you can think about picture just looks like what is highlighted in the bluish shade. And this is where your ligand. Okay, this is where your ligand is pushing your lone pair electrons for coordination, and then so that means that the one in between will have a higher energy, and the one actually axial position is kind of interstitial in between. So therefore, which one energy will go up? The one at the outside will go up, and then the one on the axis will have a lower energy. So the tetrahedral energy splitting is kind of upside down for the octahedral splitting. It's like a 3 at the top and 2 at the bottom. And this is a tetrahedral. So people sometimes put it as a delta TD. Okay, and then I can compare that once again to you for octahedral splitting because of the geometry argument. This is a delta OH. Okay, octahedral splitting, and so this is a interesting perspective for you to have a different patterns of the energy splitting. Okay, this is all about the energy splitting of the d orbital. Okay, d orbital, there are 5 d orbital. Once again, dg2, dx squared minus y squared. These are the two that are on the axis. Okay, so remember that. And then you kind of you should be able to understand this kind of the diagram differences straight away. Okay. Okay. Let me stop here.